Thank you very much. Thank you for having me. Today I'm going to talk about self-interacting dark matter. And as we all know, dark matter exists. It turns out 27% of our universe is made out of dark matter. The normal matter only accounts for 5%, and the remaining part is dark energy. Of course, we also don't know what dark matter is. I think the most well-studied dark matter candidate probably is the WIMP, called the weakly interacting massive particle. So after years of research, we haven't seen any WIMP signals yet. But I think it's a good time to think about new approaches to the dark matter problem. So we are going to take an observational driven approach. In a sense, we ask the question, for given the astrophysical observations, how can we determine the particle nature of dark matter? So after all the evidence for the existence of dark matter is from astrophysical observations and the cosmological observations, right? So let's just remind ourselves that the WIMPs are cold collisionless dark matter candidate in terms of structure formation. So we want to check whether this called CDM or lambda CDM paradigm works on different scales. Here lambda denotes dark energy. So as we all know that lambda CDM works very well on larger scales. By larger scales, I mean scales bigger than 100 kiloparsec or so. And this plot shows the power spectrum. And this solid curve is from lambda CDM predictions. And the observational data with different colors are from different observations. Of course, you see the agreement is very good. So, and lambda CDM also has very big predictions on smaller scales. By smaller scales, I mean, the galactical scales and the galaxy halos. And this plot shows this figure from numerical simulations of the structure formation of the universe. So this essentially shows the dark matter distribution in the universe. And if you zoom into this region, and you will find something called a dark matter halo. And dark matter halos are very important, right? So they are essential for galaxy formation. So each galaxy you observe are actually hosted inside a dark matter halo, including the Milky Way. From simulation, we can also understand the dark matter distribution inside a halo. You can think about this as dark matter density profile. And the density as a function of radius, as shown here. Okay. So it turns out for lambda CDM, the density profile is can be parameterized by this so-called NFW profile that has two parameters. This is called a scale density, and this is called a scale radius. And from hierarchical structure formation, we know that these two parameters are strongly correlated. And roughly speaking, for given CDM halos, you can divide the halo into three regions. If you go to very large radius, the radius bigger than the scale radius, the density goes like 1 over r cubed. There's an intermediate region, the density goes like 1 over r squared. And if you go to the very inner region, the radius is much smaller than the scale radius, then the density goes up very quickly. It goes like 1 over r. So this is called a universal density profile. In a sense, if you look at the different, the halos on different mass scales, you can, from let's say dwarf halos to the galaxy cluster halos, the density profile all follows this rule. Right? So with this, then you can ask, how can we test it? How do we know that this simulated result is consistent with observations? So how we test this? We can look at galaxies. In this talk, I'm going to focus on the spiral galaxies. In spiral galaxies, we have stars and gas particles. They are moving around. They are moving inside of the gravitational potential well of the halo. So in principle, we should be able to test the lambda CDM prediction. So let's go to like dwarf galaxies. So this is a circular velocity as a function of radius. This is a dwarf galaxy. You can see that the maximum circular velocity is about 50 kilometers per second. For our Milky Way, the circular velocity near the solar system is about 200 kilometers per second, right? So in a galaxy, there are stars, there are gas particles. So this is a stellar contribution to the rotation curve, and this is gas contribution. If you add them up, then you don't get the observed one. So that's the reason why we need dark matter in galaxies. So you need to add the halo contribution to the total rotation curve, and you take the NFW profile we just discussed, and you normalize the parameters such that you can fit this outer region. Then you extrapolate it into the inner region, and you realize that if you take an NFW profile, the theoretical prediction actually over-predicts the rotation curve. The predicted one is higher than the observed one. You can see that. Right? So the reason is that if you look at this profile, you know that if you fix the outer region in the inner region, the density goes up very quickly. It has called a Caspi density profile. Well, the data prefers to have a much shallow density profile, as shown by the red curve called a Corbe profile. Right? So this is over the core versus cusp problem that has been there for many years. But this is not the end of the story. You do see galaxies, or dwarf galaxies, which are consistent with lambda CDM predictions. This was highlighted by a paper by Oman et al. So what they do is they take a large set of rotation curve data, and they just pick up the galaxies. Then they also run the simulations. So those are the simulations are called hydrodynamical simulations. So they include the star formation and so on and so forth. Right? So and for these 4 galaxies, you can see that the data, observational data, agrees with lambda CDM predictions very well, as shown the colored bands. Right? So in the previous galaxy, you see core, and there's a core versus cusp problem. But for these galaxies, that is consistent with Caspi density profile. You can make the story more interesting if you have a bigger data set. You can pick up the galaxies, have the same Vmax, have the same maximum observed galaxies. Then you look at the inner region. So these are the 4 galaxies. You see that the Vmax is about 80 kilometers per second. But in the inner region, the rotation curves behave very different. So this galaxy becomes 80 around 2 kiloparsec. Right? So this galaxy is consistent with lambda CDM prediction. This one has a very large density core, up to like 10 kiloparsec. Lambda CDM breaks barely, and these 2 are in the middle. So it is interesting, or confusing actually, why this is the case, because the Vmax, the maximum circular velocity, is typically determined by the halo. So by the mass of the halo, which means the 4 host halos have the same mass, essentially. But why in the inner region, rotation curves behave so different? Right? This is so-called the diversity problem. And you can parameterize this diversity problem using this plot. So for each galaxy, you pick up the circular velocity at 2 kpc in the inner region, and you can also pick up what is the maximum circular velocity. So you can make a point here. So each blue point represents a galaxy. It has about 200 galaxies. And then you can see that bigger spread, when the Vmax is bigger than 50 issue, the spread is about a factor of 4. So the diversity problem is not just there for both galaxies. If you extend it to bigger galaxies, the Milky Way size is around here, even for Vmax around 300 kilometers per second, you have about a factor of 4 spread. Then you compare with observation predictions. So the black curve is from lambda CDM order predictions. This is a medium value, okay, it's shown here. And if you add barriers, those are from hydro simulations with some assumption. And so you can get this, right? So, and they are not able to explain the diversity, right? You see the observed spread is much bigger than the theoretical predictions. Now, so it means that the observed diversity in the rotation curve is bigger than what you would expect from lambda CDM cosmology. So in the rest of my talk, I'm going to show you that the diversity is expected if dark matter has strong self-interaction. The only assumption you have to make in this game is that you assume dark matter has collisions. So the collisional effect is measured by the cross-section over mass. Okay, cross-section over mass. So if this value is around 1 centimeter square per gram, which is very close to the nuclear scale, as I will show, then you will have quite an interesting effect. So you can get this number by demanding collision happens once or twice per age of the galaxy inside of the halo. So this plot shows the density profile from dark matter simulations. So this isolated simulation. You take the NFW initial condition and you put it in the computer and you wait for 10 gigayears. Right? You get a shallow density profile. This is the SIDM. So what happens? Why this is the case? Well, if you look at the velocity dispersion profile, velocity dispersion measures the dark matter speed inside the halo, or temperature inside the halo. And the red curve shows the CDM prediction. And if you go towards the inner region, the velocity dispersion is low. That is from the structure formation. And that's the reason why the density builds up. Now you turn on collisions. Collisions will transport the heat from out region to the inner region. And those inner region particles will gain kinetic energy by collisions, and they will occupy a larger orbit. And that's the reason why the density drops. So in this case, we don't consider baryons. Okay. And if you look at in SIDM, if you look at velocity dispersion profile, you see it's near the constant in the inner region. So this is a very important message, because from thermodynamics, we learned that if the dispersion is a constant, which means temperature is a constant, it really indicates that the inner region of the halo is thermalized, kinetically thermalized, in kinetic equilibrium. Right? So this actually motivates us to construct, to develop a semi-analytical approach to model the SIDM distribution in the halo. So this is very important, because in the later I will show you the detailed fit to the rotation curves. Then in this case, you could, of course, for each galaxy, you principally could run simulations to fit the data. In that case, it's very expensive. So with this analytical model, you can actually use your laptop to understand galaxies. Right? So let me just quickly go through this method. So what you do is you take a halo, you divide the halo into two regions, and the boundary is set by the scattering rate. So per age of the galaxy, if the scattering happens once, then you can divide the boundary. In the outer region, the collision rate actually is very low. So essentially, it's an FW profile, the CDM profile that we discussed. But in the inner region, self-interactions will summarize it. And you can treat actually dark matter system as ideal gas system. That's what you learn in thermodynamics. And since the isosomal, so the distribution is really given by this isosomal distribution. And I integrate out the kinetic energy. So the leftover part is this potential energy. So for a galaxy, you have dark matter halo, you have baryons. So the potential energy has two contributions. And the potential is also related to the matter distribution. Right? So this is essentially just a Poisson's equation. And you observe, for baryon part, you observe, because from observations, you know the baryon distribution, and you can reconstruct the density profile and the potential profile. So all you need to do is solve this second-order differential equation to get dark matter density profile. Right? You can only do this in self-interacting dark matter. For CDM, you cannot do it because there's no summarization picture. Right? So so we'll take this simple model to understand the diversity problem. The first step we want to look at is those galaxies. Those are the galaxies prefers to have large density cores. Right? These are the galaxies below the lambda CDM predictions. And if you take a close look of these galaxies, you realize these are the dark matter dominated galaxies. In that case, you go back to your isosomal distribution and you replace this total potential by the dark matter order potential. And you solve this Poisson's equation, very easy to solve. And you get a shallow density profile, as we show from the simulation. Right? So it's shown here, this is circular velocity. This band, the gray band, is from lambda CDM, and the blue band is from SIDM. You get a shallow density profile. So if you look at this, the outlier, two outliers over there, this like Vmax is about 70 kilometers per second. The V circular at 2 kpc is 20. So you can see this is really agrees with, the blue curve. So when I made a plot over there, then I say, wow, this must be true, right? Because it agrees with the data very well. Now, so those are the galaxies need large density cores. But to address the full diversity, you also need to explain those galaxies. These are the galaxies actually consistent with lambda CDM predictions with variables, right? So usually people think self-interactions always generate large density cores, as just as the idea was first proposed. Then if this were the case, then you wouldn't be able to explain those galaxies. But actually, the story is more interesting, because those are the galaxies called high surface brightness galaxies, which means if you look at the inner region, the gravitational potential is dominated by baryons. So baryon concentration actually is very high. If this is the case, then if you go back to the isosomal distribution, you can approximately use this baryon potential to replace the total potential. And for baryon potential, this is determined by observations, and even for different galaxies, their total baryon mass can be the same, but the baryon distributions can be very different, right? So if the radius is small, then the baryon concentration is high. If the baryon concentration is high, the potential well is deeper, and then the potential will attract more SIDM particles. So in other words, the thermalization will lead to high density profile due to the influence of the baryonic potential. As shown here, this is density of the function radius, this is CDM, this is SIDM without baryons. Now if you add baryons, and you fix the baryon mass, but you change its distribution, you change its density, then you change the density around this direction, the baryon density is high, accordingly, the SIDM so density becomes high. Right? So this is due to the thermalization. And with this, you can explain all the rotation curves. Here I show you like 8 galaxies. I picked 8 galaxies, and you can think about their outliers, and all of them have around the same Vmax, about 70 kilometers per second. If you look at the inner region, the spread is a factor of 4. Right? This is diversity. So the solid curves are from SIDM fits. And we realized there are 3 key ingredients for the SIDM to be successful. One is the scatter in the halo concentration. So some halos are just more concentrated, more dense than other halos. And this is due to the different galaxy formation histories, the halo formation history. This is what you would expect. And the baryon distributions are important. And for high surface brightness galaxies, the baryon concentration is high, and the SIDM central density is high. While for low surface brightness galaxies, and the baryon concentration is low, and so the influence on the SIDM density profile is weak. So, but the important point is that the SIDM thermalization process will tie the dark matter and the baryon distributions just in the right way to explain the data. Right? So we did this with analytical model, and I also probably with people in the reverse side, we also run some simulations to test the results. Now, this is a comparison with strong feedback. So you may have heard about that, the small scale issues are gone if you take into account, the galaxy formation. Because in real system, of course, the formation history could be complicated. There's gas can be heated up, and the supernova explosion. Those kind of nonlinear process can actually change the density profile in some cases. For example, this is called a Nihal simulation. It's a European simulation. It's quite large collaboration. So what they did is they tried to model the baryon feedback mechanism and ask, how the feedback can change the halo structure. So this is what they found. This is again the 8 same galaxies. So the gray curves are from simulations. What this simulation does is that the feedback is so strong it can blow away dark matter, right? But then this simulation can generate some density cores. You can see that. But because the feedback is so strong, you cannot explain the high surface brightness galaxies. So there's a physics reason behind this, because if the feedback is strong, blow away dark matter, you also blow away stars, because stars behave like the collisionless particles. So the feedback is so strong, you cannot explain the galaxies in this region. But well, so summarization feature in SIM just give you the right fit. And the analysis is based on this analytical model, and you may wonder whether it is correct or not, because in this model we just assume it's equilibrium. We don't take into account galaxy formation, the dynamical process into our model. So some people, some simulators, Andrew Robson at Durham University, and he kind of doesn't believe it. He just run the simulation actually to falsify this. So then he sent me some of his results. Then I say, well, okay, I can check the analytical model for you. This is what you get. So the red curve is from analytical model prediction. The blue curve is from hydro simulations. Okay? And this is the baryon contribution to this NFW profile. So the agreement is remarkably good. So for SIDM, because of the summarization process, the final dark matter distribution is sensitive to the baryon distribution, but not to the formation history. Okay? This is what we would expect. So you can take bigger samples. So very recently with my student and my colleague Manoj Kapnihana's student, we analyzed the data for 135 galaxies. This is the largest data set we can get for the purpose. And we did like 2 independent data analysis, use different methods, we get the same result. So the agreement is very good, and you can see this is different mass beams, and you can see for each galaxy you can fit the data. So I show you an example to highlight the result. So this one actually is the worst fit in the data set, because if you read off the chi-square per degrees of freedom, it's about 44, right? If you look at this number, you will charge your fit. But if you look at the agreement, it's really good. The reason why you have the large chi-square value is due to some data points there's negligible errors. Right? So this just want to show you that for each galaxy, we can get a fit. So far, we mainly focused on the diversity aspect of galaxy rotation curve. And you can look at the rotation curves from another perspective. And for example, this was kind of highlighted by Stacy McCoy and his company. So what you do is, for each galaxy, you can look at the total acceleration, which is given by v squared over r, as a function, the baryonic acceleration, right? And for each galaxy, for each data point, you can calculate these 2 values, and you put the data point in this plane. And for 135 galaxies we discussed, then there are about 3,000 data points. So it's shown like a blue one. And there's some distribution over there, but actually it's pretty tight. The distribution is pretty tight along this curve. And this curve is given by the functional form proposed by Stacy et al. And actually, if you are familiar with this Maunder story, this essentially is a Maunder story, right? So this G dagger is fundamental acceleration. So in the original Maunder story, is that for the acceleration below this G dagger, then Newtonian gravity breaks down. So you need to modify it. So this is a modification proposed by Milgram et al. Milgram himself in 1983. And so if you fit the data, and you can read off this G dagger, it's about 10 to minus 10 meters per second squared. And if you look at the literature, actually is very small. So the scatter is very small, right? So this is purely from observation by fixing some mass to the light ratio. And since we fit all the SIDM data point models, then what the SIDM will say about this correlation. So this is the SIDM from the SIDM, from our fits. So we get this G dagger very close to this value, and the standard deviation is also very small. So in other words, SIDM explains both the diversity and the uniformity of the galaxy rotation curves. And we also talked about why there's acceleration scale, and it actually comes from the hierarchical structure formation. For each halo, you can get as an acceleration scale. All right, so far we focused on the spiral galaxies. The mass is in this range, 10 to the 9 to 10 to the 12. And you can ask, how the story changes if you go to galaxy clusters. Those halos are about 10 to the 14 to 10 to the 15 solar mass. And it turns out that there are density cores in these galaxy clusters. But to fit the data, it turns out that the cross-section has to be small. It will be about 1 order magnitude smaller than what we need for those galaxies. And so people typically, call the bullet cluster is a strong constraint on self-interacting cross-section. It's not, actually. The stellar kinematics have the strongest constraint. So if you have an SIDM model, then you have to meet 2 challenges. One is to generate large enough cross-sections, nuclear scale cross-sections, on small scale, on dwarf scales. Then your velocity, your cross-section should also have a velocity dependence. So how do you achieve this? So you can imagine that there's dark matter interacting with the dark photon. And so the interaction is this Yukawa interaction. And so there are 3 parameters for this Yukawa interaction. And you fix the coupling constant. Then you demand that your theory to explain all the observations from dwarf galaxies to the Milky Way-sized galaxies to galaxy clusters. So there's a closed region that you can explain all of them. And from closed region, you can read off what the dark matter mass is and what the mediate mass is. And in this best fit region, the scattering cross-section really goes like velocity dependent, right? So this result, to me, is very remarkable because in principle, we can measure dark matter mass and mediate mass without detecting dark matter directly. This doesn't rely on the assumption that dark matter has to come up to stand up. It's purely dark sector stuff, right? And you may also think that we're crazy to think about dark matter as collisions. But we have familiar examples in the visible sector. Electrons have collisions. And then like nucleus have collisions. And even like in plasma physics, these ions have collisions. But for ions, actually the potential is exactly the Yukawa potential because the photon has a mass and the ions move very slowly. And so this is in a non-relativistic limit. Then if you look at the nuclear physics data book, people measure the collisions between protons and the neutrons. And again, you can see that as a velocity dependence goes like this. So this is the SIDM. So you can just scale the cross-section down a little bit. So I think I'm running out of time. So I just very quickly go through it. So SIDM did a very good job. And you can look at the electric detection signals. So this is a collaboration with the Panda-X experiment. And you can see the signal picked more towards low energy. And you can also look at the tidal signals. Instead of, aside from the monojet signal, you can look for displaced electron jets. It's very different from the Ewing signals. So let's just summarize. So there are strong constraints from dark matter interactions with stellar model particles, and there are strong hints for dark matter self-interactions. So today, SIDM is the only mechanism actually has been shown to explain both the diversity and the uniformity of galaxy rotation curve. And this issue has been part of the field for more than 20 years. With only one more parameter, one cross-section, right? And the results are robust to feedback galaxy formation due to the collision of summarization. I'll just skip this. Thank you very much.
Okay, time for questions or comments.
So a quick question. So in general, how much cold dark matter, non-interacting dark matter, can this model endure? For instance, if you have a negligible cold dark matter, non-interacting dark matter into this picture, I think it still survives. Or it doesn't change the story.
So here we made an assumption all dark matter is self-interacting.
Yeah.
So you may wonder, some portion can be self-interacting, some portion not self-interacting, right?
Yeah.
So I don't think so the story will change a little bit, but I think no one knows at this point how big the change can be. But this is in the middle, and probably if some portion of the dark matter self-interactions, maybe your cross-section has to be bigger, to accommodate all these observations. Right? So yeah, please look and run the simulation actually to check that.
I just wondered your slides about the feet. You said is degrees of freedom is 44,
yeah.
And then you still think it's okay, but then you blame and the big chi-square per degrees of freedom due to the small or error. But then statistically, it doesn't matter. Right? You fit per degrees of freedom, match the number to judge.
I know what you're saying. I think that the issue that the question is, do you trust those data points or not, right? So there's no error. So, I mean that's the only thing. But
so you trust your model better than the data.
Yes.
Okay. If you have that confidence, okay.
Yeah, because you also look at the overall features, right? So each galaxy essentially the agreement is. I mean, for this particular one, it's really there's no error bus, right? I even think an observer don't believe there's no error bus, right?
So you get a complaint from them?
I don't get a complaint from them.
Hi. So to explain the diversity of the rotation curve, you mentioned that it's very important to take into account the gas fraction in the innermost region. So whether it's low surface brightness or high surface brightness.
Yeah.
Right. So I was wondering, when you do this fitting for 135 gases, do you check this gas fraction is a fitting parameter, or it's fixed by observation?
Oh, okay, good point. So it's not just the gas. So usually for bigger galaxies, the central region is dominated by stars, but for some dwarf galaxies, it's dominated by gas. So what you do is, the circular velocity goes like halo contribution, stellar contribution gas. And this is pretty much fixed. For stars, there's one free parameter called the mass to the light ratio, because in observations, you only can look at the luminosities, right? Then you have to convert the luminosity to mass. So for each galaxy, of course, you don't know exact value, but from the population synthesis model, people have some idea, how big it can be. So in our analysis, we give a bigger range. Then we just ask what the fit tells you. So in my backup slide that I can show you later is that all these preferred values from fits is consistent with population synthesis model you would expect.
So if you have a figure showing all the data observation data points, so for Vmax versus replication velocity, right?
Yeah.
So and you say that the observation in the data points is scattered a lot. So and I was wondering that figure for the observations with higher rotating curves, so they are all belong to say high surface brightness galaxies.
Okay, yeah. So very good. So you're asking, for galaxies, like this, right? So in this region, whether those are always high surface bright galaxies or not, right? So otherwise, if that's all due to dark matter, then there will be an issue. So the answer is yes. If we go through 135 galaxies, it looks like the galaxies in this region, most of them, like 90% of them are high surface bright in this galaxy. There are some galaxies, especially low surface bright, several low surface bright in these galaxies, actually don't have a lot of matter in the central region, but the rotation curve can go high very quickly. So we explain this due to the scattering in the halo concentration. So this is what you would expect in structure formation. Some galaxies are just more dense than other galaxies. So that you can explain that. So for all the 135 galaxies we analyzed, I will show that the plot showing the halos are consistent with lambda CDM, the lambda SIDM predictions in terms of the concentration mass prediction. Sweet.
Actually, just raise a similar questions. I remember one of your paper you published a result of this is sigma divided by n
Yeah.
versus with velocity dispersions
Yeah.
And then they have several data points based on different satellite galaxies. And
This one?
Yeah.
Oh,
And I have just one question: is any one particle models can satisfy all the data?
Yeah, it's good point. Okay, so this paper is published a little bit earlier than the analysis I showed you the diversity problem. Because in this, but what we did was we didn't fix the cross section. We just asked what data prefers a cross section. So overall, you can see a lot of scatter, right? So there's a spread in terms of the cross section. Actually, that scatter reflected the diversity problem I discussed. So it turns out for all those galaxies, you can fit it with one cross section. You can see the error was large. But this diversity can be explained actually by the concentration mass relation in the background distribution and so on and so forth. So later we find that all this galaxy can be fit with a cross section 2 or 3. And so there's no actually the issue. But back then we tried to fit a particle physics model as shown here, this beta curve. On average, this curve passes through most of the dwarf galaxies. But then on the cluster scale, it passes through here. So this is shown here. There's a constant cross section on small scales, but drops on the larger scales. But that's enough to explain the diversity.
Okay, any more questions? Okay, so let's thank the speaker.